Welcome back everyone. In this video, which is optional, we are going to be taking an advanced look at force vectors. And what we're doing here is something that if you happen to be in trig, you might have heard about, but if you're taking Algebra 2 Honors, you probably haven't seen this yet. So this might be something new. And again, just a warning that this will not show up on a test, it's just kind of for fun. Okay? Now what we said in the previous video on Coulombs law is that if I have two positive charges, charge Q1 and Q2, and I want to know the force on charge Q1, that's the force of 2 on 1, what I've got to do is draw it and then kind of ignore the fact that there's a negative sign, or rather if I multiply Q1 times Q2 over R squared, that there isn't a negative sign, that it's going to be a positive value, even though the force is going to the left. And so what I want is kind of a systematic way to not have this problem. And so what this will do is allow me to do a full calculation of what the force is going to be, because really the force is a vector, okay? And when I was writing Fe equals K Q1 Q2 over R squared, I wasn't really giving the whole story. It is a vector that is, it has a magnitude of K Q1 Q2 over R squared, and it has a direction. So if instead I say that this is the electric force, okay, between 2 and 1, then I need something called a unit radial vector between 2 and 1. Let me back up a little bit. First of all, let's talk about what we mean by a unit vector. Okay? So a unit vector is a vector of length 1 in a certain direction. What direction, you might ask? Anyone you want. That's the use of a unit vector. Okay, now most of what we're going to be doing with Coulomb's law will be confined to the x and y directions. And so this brings up two different unit vectors. First of all, we have the illustrious unit vector I hat, which is a vector of length 1, which goes along the x-axis. Okay, so if I wanted to draw I hat, it would go up until 1. That is I hat. Now, why do we put a hat on it? Well, some textbooks will write it like this. It's I, but where does the dot go? And is there an arrow? And some textbooks will write it in boldface, but how easy is that for me to do? Not really. And so what we do for unit vectors, or at least what I will do, is write it like this. This is I hat. That's what the little caret is. Okay, now there's also a unit vector which goes along the y-axis, and we call this one j hat, which is a unit vector of length 1 that goes along the y-axis. And so what that would look like is something like so. There's j hat. Okay, let me move my label. There's I hat and j hat. Okay? And they are perpendicular to each other because they go along the axis, and they each have a length of 1. Okay? So that is an introduction to unit vectors. We can also, if you want, write k hat, which is the same thing, but now we're getting all three-dimensional, and this goes along the z-axis, which I don't even have in my diagram. Okay, so most of the time I hat and j hat is just fine. Alright, now let's say a little bit more about what a unit vector really is, because it can be in any direction. Okay, so basically if I have a unit vector r hat, well, that is a vector of length 1 that goes along a radial axis. You might see where I'm going with this, that in all of our force equations we have blah 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 over r squared. Well, what does that r really represent? If I have q1 and q2, r represents a vector between the two of them. And up until now, we've only been talking about the distance r. Okay, so now let's say that I want to know the force that 2 is exerting on 1. So again, positive, positive, and this is the force that 2 is exerting on 1, and it is a vector. What I can draw here is a vector r21, which is a vector from q2 to q1. So what does that look like? It looks like that. That is r21. Okay? Now, r21 actually has two parts. It has a magnitude. What is the magnitude of it? The magnitude is its length, and we already said a moment ago that that is simply r, the distance between the two charges. Okay, so far so good. What is the direction of r21? Well, there's a couple of different ways that you could describe this. First of all, you could say that it is in the negative I hat direction. And that is totally correct, because if we start at q2 and if we march to the left, we're going in the negative I hat direction. Okay? The other way that we can do this that is equally legit is to say that we are going in excuse me, the r hat 21 direction. And here's why this is useful. If I have charges that are at a random angle, and this is charge 1 and charge 2, well, now I can say that r21 is the vector between them, okay, and r hat 21 is a unit vector in the direction between them. So r21 could have a length of, maybe r is 3 meters, I don't know, but r21 is only going to have a length of 1. Okay, so this is kind of weird. It's probably best to see this in an example, but there's one more thing that we have to do. We have to say a little bit more about what r hat 21 really means. Okay, now this is a definition, and if it's kind of out there, you can just smile and nod for now. Okay, but what we say is to get a unit vector in the direction between 2 and 1, what we need to do is take the vector itself, r21, and we divide by the length of that vector. Okay, so this is the length of r21. Let me give you a concrete example of this. Okay, let's say that I have q1 right here, q2 right here, and this is at x equals 0, and this is at x equals 5. Okay? Well, r21 would be equal to, believe it or not, 5 units in the negative I hat direction. That's how I get from 2 to 1. Okay. Then the magnitude of r21 would be its length, 5. And if I divide those two, I will get r hat 21, which is negative I hat. And that's a fancy way of saying that if r21 is a length of 5 going from 2 to 1, then r hat 21 is a length of 1 going from 2 to 1. Okay, so far so good? Maybe. Now the last step is to take this definition right here and to plug it into Coulomb's law, so that the electric force K Q1 Q2 over R21 squared times R hat 21. And this is the force between 2 and 1. So now what I do is I take this expression for R21 and plug it into here. Okay, so here we go. Final answer for my electric force between 2 and 1 is equal to K Q1 Q2 over R21 cubed times R21. Wow, that's crazy. So down here, this is a length. And right here, this is a vector. Okay, let me give you a physical example. Here we go. Q1 is a charge of 5 microcoulombs positive sitting at the origin. Q2 is a charge of, let's make it positive to start with, 10 microcoulombs sitting at x equals 5 meters. We'll just stick with this, okay? This means that to calculate the electric force between 2 and 1, I take K, Q1, Q2, and I divide by the length cubed times R21. Alright, let's try this. Alright, K is easy. Q1 is easy. Okay, now I'm going to leave my plus 5 microcoulombs in there. And Q2 is plus 10. Okay, now let's think about this. What is the distance between 2 and 1? In other words, what should I put in for R21? Oh, well, clearly they are separated by 5 meters, but I have to cube that. Okay, so they're 5 meters apart. Now, R21, on the other hand, is a vector which goes from 2 to 1. And in this case, it's equal to negative 5 meters in the I hat direction. So negative 5 I hat. Now here's where the beautiful thing happens. Notice I get a negative sign. If I put everything in this correctly, I will get a negative sign out of this. And when I calculate my force, I'm just going to do this real quick. Alright, I'm going to get a numerator. All of this stuff is going to turn into 0.45. Okay? Now, I'm going to get 125 down here. And then I'm going to multiply that by negative 5 I hat. I'm getting rid of all my units. So that actually just turns that back into 25, and I get negative 0.018 newtons in the I hat direction. Okay, so notice how beautiful this is. It's giving me the direction, right or left, and it's also giving me the direction, I or J. So now I know everything I need to about this force, and I didn't have to try to guess the direction. Okay? Now, a bit later on, I'm going to do another optional video, and hopefully you'll see the power of it when we have a situation like this. Here's one charge, and here's another charge, and here's a third. How do I find the net force on this guy? Okay, so let's say positive minus positive. This problem is a huge pain in the butt. So if this is charge 1, charge 2, and charge 3, we want to find the net force on charge 1. This is a gigantic pain in the butt because what is 2 doing to 1? It's going this way. It's some random angle I don't know. What is 3 doing to 1? It's pulling this way with some other random angle I don't know. How do I find the net force? Well, I have to do my parallelogram rule, and I have to set up a table, and it's a huge mess. But with this new method, this is a little bit easier. Okay, so I hope that you got something out of this. If not, at least you have an introduction to unit vectors. Okay, now in the next video, we will talk about electric fields.